Hi everybody. So I posted a video the other day where I showed you a Mandelbrot render, and that's because I finally got my circuit running, but I didn't feel like making a video explaining how it worked right then. I just wanted to get out a video showing you, hey, it rendered something. So now I'm going to explain today the fixed point notation that I used, and I'm going to go over how the circuit actually works. So first off, I kind of want to explain how Mandelbrot works. And the way Mandelbrot works is, if we go here into the sheet, we have some real and imaginary constants that we put in, or yeah, well, they are a constant that we give it initially. So I initially gave it negative 0.3125 and positive 0.0625 for the real and imaginary part. What it did is then it squared A, it then squared B, and then did a squared minus b squared, and it added back the original a, which is in this column. This column contains all the original a, and this column contains all the original b, which you can see are these two right here. So that's where it grabbed the a0 from, is from over there. And then it calculated that value. Then it took a times b, and then multiplied it by 2 and got that value. And then it took that value and added to it b0. So you can see, whenever we generate a new real or a new imaginary, we have to add back that constant of a0 or b0. And then this number and that number now become that number here. And now these get plugged in to the next line, and you iterate through this. Okay, so as we iterate through this, you want to see if these numbers blow up or if they don't. And as you can see, these numbers actually start converging. It starts a little funky, and then as we run more iterations, you can see it's starting to lock in on a number here. 0.041602. And then you can see the same thing is happening here in the new real. It converged onto it, or converged, onto a number. So that means this number belongs in the Mandelbrot set because it didn't blow up. And the way that we can check if it blew up is we can say this cell is equal to this cell plus this cell, and we can say if well, I did not like that. This is equal to this cell plus that cell. Oops. There we go. So if we add these two cells together, actually wait, we need to square them, sorry, equals that squared plus, whoa, what did I just do? That squared plus that squared. There we go. And now we can check if that is greater than 4. So if that number blows up greater than 4, or if that number ever gets greater than 4, it will blow up. So all we have to do is now stack that down, and you can see that this number never blows up. This number, in fact, stays flat. And so what you do with your escape sequence on the Mandelbrot, what it tells you how you color this thing is, if you run 16 iterations, but it blows up before 16 iterations, it blows up on the first iteration. If this first number is greater than 4, then immediately it gets white. And the more iterations it takes to before it escapes, or before it throws the flag saying it's greater, or it blew up or something like that, the more iterations it goes means the more confident it isn't to blow up if it's less than 4. And that means you're going to color it a darker color so that you can see it on the screen. So if I'm only doing 16 iterations, if it didn't blow up at all, we get like the blackest black. If it blew up on the last stage, then we get like kind of black. If it blew up on the second last stage, then like gray, and then you'd work your way up towards white if it blew up immediately, like on the first stage. And so that's basically how the Mandelbrot set works. So now we can try, like, say if we did like positive 1. Oh wait, Control Z, sorry. If we did like 1 and 1, then we'd have to copy those numbers into here. And then this. I could say this cell equals that cell, and this cell equals that cell, and I could just stack them. Ah, shoot. Control C. I have to put the constants in here. But you can see, like, that's all as far as I'll go because these numbers are blowing up. You put in +1 and +1 and you can see it's starting to blow up. Like on the first stage is greater than 4. But like if we put in like here, like -0.25, now it didn't blow up as much. And if we put in here like 0.5, now it gets a little bit darker colored, and because it blew up on the third stage. And now we can put in like something really small, like 0.25. Still doesn't blow up as much. Oh, but that's still because of this. There we go. Sorry. I should be able to pull this down now. There we go. Okay. So now you can see this converged. If we put in like, oh, let's try putting 1 back in here. This converged. So like we could put in a bunch of different numbers and test to see if our circuit works when we build it. But now we need to be able to represent positive and negative numbers, and we need to represent all these freaking decimal points. So how do we do it? Well, I'm going to take you to this spreadsheet. And basically, the way my number system works here is it's 16 bits. The top 4 bits are integer bits, and then after that, they're all radix bits. That might make it a little bit easier to see. Yeah. So, you can see here, these have the value 8421. Then half, quarter, 8, 16, 30, all the way down to 1/4096. And so now basically you can put in numbers in here and you can form a number. So if you wanted to figure out what your number was, if you had like 1011111100 like that. So if you had 233 C in hex, then that's what the fixed point notation actually is. Okay, but now we need to be able to account for positives and negatives, so how do we do this? Well, you see this value of 8 isn't actually a value of 8, it's actually the sign bit. So if that bit is on, we need to perform a 2's complement conversion to actually know the magnitude. So here's an example of that. If I have, I was doing a bunch of conversions making sure this worked properly. So if I had, a number in A and a number in B as F100 and F000. If this is what my Mandelbrot was outputting, I needed to know if this was the correct number, like what the actual magnitude is, so I could put this into my Excel spreadsheet to check it. So I needed to convert it. So F100, as you can see, F100 like that. We invert and add 1, while you 0000, 111, 0, and then all these would become 1s, but then when you add 1, it carries over and becomes that. So when you convert this, it actually becomes 0F00, and so this number here is telling us that it was actually negative 0.93750, because when you plug in 0F00 here, 0, 1, 1, 0, 0, you can see that we got 0.9375, but we had to do the 2's complement conversion on it, which means that it was actually negative. So that's how we represent, like F100 is how we represent negative 0.9375. So this is the kind of conversions that the calculation has to be able to do. And with fixed point is nice because in Mandelbrot we know our precision that we need, right? We know that we only need to be able to check a sign bit and up to a value of 4. So that means we know we only need 4 integer bits, and if we were to add more bits to the system, we still only need 4 integer bits. That just means we can add more radix bits. So if you were to do this with 32 bits, you can have 4 bits dedicated to your integer and 28 for your radix. And you can get some crazy big precision out of that. So floating point, or Mandelbrot is one of those things that if you build it all with fixed point and like it's able to actually be implemented properly, it would be a lot faster than floating point because you know your precision. Floating point now is just like what every processor has, and they're such fast units that it's capable of doing those calculations. But if you were to just have a pure integer unit versus a pure floating point unit meant to be doing the Mandelbrot, the integer unit will be faster. It's just that integer units are very specific, whereas floating point can be done for a lot of general purpose things. That's why a lot of CPUs use that nowadays. But when I'm building a hardware ASIC, I don't need a general purpose. I want something that's fast for doing what I want. So that's what I'm doing here. That's why I set first 4 bits as integer bits, because I knew it's sign, and then up to a value of 4 I needed to be able to detect as my escape sequence. So if it was greater than 4, then obviously I'm out. It's getting the dark or the whitest white it can, well, depending on how far it went along. And I just need to know if it was positive or negative for anything else. So, and then obviously these bits, I mean, obviously you need to be able to check up to 4, so yeah. And then all the decimal places. So now that I explained kind of how the Mandelbrot is computed here with a squared, you calculate b squared, then you do the a squared minus b squared plus a, then you do 2ab, and you do 2ab plus the b naught, and you run that, you iterate through that. Now I can show you the circuit. So basically, we open this, we can see here that we have the a naught and the b naught that come through. And we can see that we have A and B here. A and B, this becomes the next A and the next B down here. So this would feed into the next one here, and that would feed into the next one here. You would just chain these together. But you need these original A naughts and B naughts coming through. So basically what I did here, to get A squared, is I took the absolute value of A, and I squared it, because you're just going to lose the sign anyway, so there's no need to XOR the sign back on. So you just take the absolute value, don't deal with the sign because it's squaring, and you get rid of it. You do the same thing with B. You take the absolute value and then you square it. And this fixed point multiplier, the way it works, is this is a 16-bit value, this is a 16-bit value. The multiplier outputs a 32-bit value, and we still need to somehow retain where our decimal point is. So what I do is I take the top, I take the bottom 15-bit or 16 bits, and I somehow just take the 4 off of that, and then I take 8 bits there, and another 12, 13, 14, 15, another 4 bits there off the high side, and that's how I retain my decimal point. So with fixed point, you just have to retain your decimal point when you're doing the multiplication, because all of your bit width's double. So if I go back now, you can see that the multiplier is just doing the fixed point multiplication. That's why it's called fixed point mult. And then it's just outputting here. So now what we do is we do a squared minus b squared. So a comes in squared minus b squared. Carry in gets tied to 0 because we don't need the carry in for subtract or for add. And then we add back in a naught, and you can see this a is a naught, so we're adding in a naught to that, and that becomes a new real value. Now the next b value, or the next imaginary value, takes 2ab. So we take the way it works is a and b come through here, we take a and we take the absolute value of it, we take b and we take the absolute value of it, we multiply them, and then we left shift that by once to do 2ab. So left shifting once gets you multiplied by 2, and then we did the a times b there. Then what we do is this should have a sign on it depending on what the sign was on the one or the other one. So that's why I split these off, and we took the sign bit there and we took the sign bit there. We XOR the sign bit and decide whether or not it needs to be complemented or not, whether the output was signed or not, basically. So 2ab, a or b can be signed values. It could be 2 times negative a times b, 2 times a times negative b, 2 times negative a times negative b. So depending on what those signs are, you need to be able to cancel them properly, and that's what the XOR does. Then we need to add b naught to that. So then you can see b naught comes through, down, and gets added in here. So we do this plus b naught, and that becomes our new imaginary number. And we allow it through at all times unless the output is greater than 4. If the output is greater than 4 on that stage, we're not going to pass anything through. We're going to pass a 0 through. Oops. And the reason for that is we don't want anything. We don't want to be calculating down the stage, and we don't want any other stages to be throwing if it's greater than 4. We want only the first one that says it's greater than 4. That's one we care about, so we know which to color it. We don't want multiple duplicates saying, well, if the first one's greater than 4, and then if we were to throw those numbers down stage and it also produces values that say it's greater than 4, then how do we know which one to pick? with this solution, it gives you only one value if it's greater than 4. And the way you compare is you take the output of b, you take the absolute value, and then you square it. And you do the same with a, and you take a squared plus b squared, and you check if that's greater than 4. Because ideally you want to check if a squared plus b squared, or you want to check if the square root of a squared plus b squared is greater than 2. But if you just square both sides, you get a squared plus b squared greater than 4. So it's easier to do that than doing a square root, obviously. Just change the constant you're checking for. Although that did require us to use one extra bit in the integer to do that. If we only had to go up to a value of 2, we would have only needed 3 bits in the integer, and we could use square root. But square root is not easy to build. It takes a lot of time. Like, it's linear. I don't know what the big O notation is for that, like the actual time complexity for the square root is, but it's similar to division, so it's slow. So here's how it actually generates these values. And you can see here that it takes the constant value that gets fed in and gives it to each one. And we pass through the generated value to the next and the next and the next. And then, like I said, if it is greater than 4 in the first one, then it gets 1F, that's the whitest white. Then 1D is like turning gray until like we get towards the right here, which is 0 is black. So 1 is like dark gray, then lighter dark gray, then light dark gray, you know, and then like it works its way towards white that way. So if it didn't blow up at all, it gets the darkest dark. And I'm only doing 16 iterations here, which you can obviously do a lot more. Now you may be asking, how does it know what values to feed in and generate onto the RAM? Well, it knows those values because I have to generate those off of my mapping of my screen to my RAM. So let's just run this real quick and let's show you what I mean. Got to reset to -2, enable, and then let go of the reset to -2. And you can see it's generating an image. So what I had to do to actually get this to work is I had to say this bottom right corner here is actually -2 minus 2i. This corner is +2 minus 2i. This is +2 plus 2i, and this is -2 plus 2i. And then the center here somewhere is 0. So then I had to map 128 pixels across that -2 to +2 on each axis. So 128 divided by a distance from -2 to +2 is 4. So I had to do steps of 1/32. So basically I said this pixel is -2, then I do -2 plus 1/32, and that tells me my next pixel value. And I keep adding 1/32 until I get to 2 minus 1/32, and that's this last pixel here. So I can't quite hit 2 on that, and the reason is, if we actually look in here, so I was mapping out a screen here, so like our center here is obviously here, and that means the pixel values that we're defining are actually lying on these boundaries, right? But we don't want to do that. We want to define this space here as the pixel. We don't want to define the boundaries here as the pixels, right? So we really don't have a 0 pixel, right? We have 4 center pixels like that. 1, 2, 3, 4. Okay, so to do that, we can't say that this is actually 2 plus 2i. It's actually +2 minus 2i plus 1/32 I. Because it's not quite that. We have to generate this. We can't just be putting it on that boundary, so we have to put it inside. So okay, just a quick note, when I was recording this, I wrote that when we were talking about where the boundary of the pixel aligns, I added this +1/32i to the wrong thing. You don't want to add it here. You want to add it to the 2. So if we get rid of this I, we just want to add +1/32. So we have +2, and instead of adding it, we're 1 less than +2. So we're actually going to change this here to a subtract. And like that. So we have 2 minus 1/32 minus 2i is actually that pixel. And then up here, when you have when you're looking for the positive boundary, then yeah, it's the same thing. Where now with the +2i, it's actually +2i minus 1/32 I, and this is minus 1/32 off the 2. So we have 2 minus 1/32 here, and then 2 minus 1 over 32i there. So we can't quite hit the top, and we quite can't hit that corner, but everything else inside we can hit because we needed to define those boundaries. Sorry about that confusion. Yeah, that's about it. I can go inside here and show you. So if we stop, open the circuit here. So all this has to do is it has to map from -2 to just under +2. And if you know, our decimal point is here, so it's saying 1 point, well, like 111110000, you know. So like it's so close to being, it's like saying it's 1.99990 in decimal, right? So it's just about 2. And this E00, if you want to calculate what E00 is, well, we'd say E000. And if we look up here, E is 14. So we know that's 1110-0-1234-1234-1234. We know that the most significant bit's on, so it's signed, so we have to do 2's complement. So we have 0001 dash, and it would be all ones, which we know. Then when we add 1, it would carry over to like this. And so the 2's complement conversion is this. So we can see that E0 is actually -2. We had to do 2's complement on it, and the magnitude is 2, which means it's signed to it's a -2. And so you can see that we're actually drawing. I'm saying draw from -2, or like reset to 0, or reset to -2 sets it to -2 on the frame, and then it says output that value, and then also make sure that you have to output x and y coordinates as you're outputting the values for the imaginary and the reals. So x0 and y0 need to map to -2, -2. So if I start the circuit here, if I enable it and I reset to -2 and I clock it, you can see that we reset both to -2. If I clock this once, you can see that we generated the next imaginary address, or the next real, sorry. The imaginary stayed the same, and the x-coordinate went up. Now the x-coordinate will count up 127 times before the imaginary goes up 1, because we have to scan 128 across, and we're already at 1. So if you can see, like if I just kept clocking this now, we're just going to be adding 080 to this number, imaginary number, 1 at a time, as this x-coordinate up there increases. And this is going to take a long time, but if I do fastest mouse clicker, alright, and I do P, you can see that now we can see that the bottom is actually moving up. And you can see when it hits, I'll do it here, you can see that it hits 1980 right there, and then it rolls over. Oh wait, no, sorry. It hits 1F80, sorry. Not 1980, 1F80. Ready? Right here, it threw that it was equal to here, and now it's going to roll this next one down here over. Like that. And now this went back to, when this goes to 0, this one increments up. And because of that, the y coordinate had to increment up as the x coordinate went back to 0. So now we're saying we're up 15 y positions, and now we're back at x equals 0. And then this is the imaginary value there. So the Mandelbrot needs to calculate what it should blow up to at that imaginary value for that pixel address. So what this does is it maps the pixel address to the imaginary values so that we can feed them through our Mandelbrot set. And this is how you can also implement zooming and panning by adjusting these parameters here. The E00 and the F1F80 tell you where your screen is centered, right? So if we add offsets of our zoom multiplier to this, we can move our screen to the right or to the left. Or if we do it down here, we can move it to the up or down so we can pan around. If we change the zoom factor and cut in half these E00 and the 1F80, keeping the sign, then what we can do is we zoom in by like a 2-time zoom, and then we can pan around in that as well. So what I'm adding now is the pan and zoom abilities to this. So if I come back out now the way it works is it outputs the x and y coordinate. I had to align the y coordinate to being the bottom down here, otherwise this image would have been flipped if I didn't put this inverter here. And then there's this graphic-gram, which the way the graphic-gram works, it says how many data bits are there. Well, there's 16 because I'm using the high RGB color scheme where the most significant bit gets 1, and then there's 555 for RGB. And since I'm doing grayscale, they all get the same value tied to each other like that. So R, G, and B values get all the same value. That's how you get grayscale, and you get 32 levels of gray like that. Well, since I'm doing 16 iterations, I decrement 2 values at a time, basically. So if it blows up, it'll say, you know, like, make it 31, then do like 29, then 27, and it decrements 2 at a time until it gets to 1, and then if it doesn't blow up at all, it gets 0, so the dark is dark. That's the way I decided to do it. And yeah, so the width in pixels is 128, and the height in pixels is 128. So basically the address here is the low 7 bits are like the X, and the top 7 bits are the Y. And so I had to, for some reason I needed to hook it up like this because I outputted 8 bits, I guess, I don't know. But yeah, I had to use these splitters like that. And so yeah, you can see the color here comes from over here. So if we run this now like a lot more slowly, like 20, when we start, we have to reset to -2, enable. That then starts the graphic RAM up, and then we do that. And now you can watch this, and it's telling you it's still running pretty quick. It does take a while to draw though at this speed. But yeah, you can see which ones it's telling you to blow up, and it looks like a bunch are on at the same time, but there's really only one on at once. It's just that it's going so quick. And then the color is coming out here. You know. And you can see this will start going down to 0 as we start getting like closer and closer into the set, but it's going to take a very long time. And I'm pretty sure, oh no, we can't. That's what sucks about this compared to Logisim, where we could open up and see what's going on inside here in Logisim. But you can see, here's the numbers coming across, and then it increments this. When this gets to 1F80, this one increments. And then that goes back to E000, and then does it again. And these are all the constants coming in, and then it's calculating whether or not what it should do with that. And so you can see how quick those are updating. That's why you can't really quite see these green lines turning off and on that quick. And yeah, that's how it works. So, like I said, coming up next is the zoom and pan abilities. And yeah, if you guys want, now that you know how it works, you can actually go to my GitHub, which is here, my repositories. So I have a 16-bit fixed point mandelplotter. I'm not really good at using this, so I always just upload a new branch with the date, and then inside this folder here, Mandelbrot, you'll find mandelbrot.dig, and that's the you need to run this file here, so you need everything in that folder. And so you just download this, open that folder, and then open up digital with that file, and it'll run. So here's how the instructions: download digital, open Mandelbrot dig that found inside the Mandelbrot folder using digital, start the simulation. The clock is immediately running once you start the simulation. Put a 1 on the reset to -2, put a 1 on enable, and then put a 0 on reset to -2, and that's exactly what we did. We put a 1 on reset to -2, we put a 1 on enable, and we put a 0 on reset to -2. And that's all the instructions are to get this thing running. I am, like I said, adding zoom and pan, which will use the WASD to move around, and I'm Japan, and I think maybe like the up and down keys on the arrow, like the arrow keys on the keyboard, maybe will be zoom in and out. So it'll be kind of fluid to zoom in and out and pan around. And obviously, digital is really efficient at how it calculates things. So like a whole screen, like if you want to see, like if we set this to like, I'll set it to 10,000. Okay, start, reset to -2, enable, and you'll see like it's actually pretty good. So I'm going to be able to render a frame, say now that the frame is rendered, it throws a flag out, it knows when it's done. I'll be able to zoom in and then pan. Like if I zoom in, it's going to render a new frame, and then if I pan, it's going to render a new frame. So every action I do, it's going to render a new frame, and you're not going to be able to do a new action until it's rendered the frame. But every frame will take the same amount of time to render because it's fixed point. The notation isn't changing. It takes the same amount of cycles to do everything once it generates the new constants for everything. So like it'll be constant time to zoom in. Like so, it's going to be really efficient at actually zooming in and all that stuff. It's not going to slow down as you zoom in, like what happens with floating point. So yeah. thanks for watching, I guess, if you actually made it this far. And yeah, I hope you stick around to see the progress that actually happens with this. So peace. And also thanks, shout out to Josh for the music that's on this video. The music from him is custom, and he writes a lot of it, and he does commissions. So if you guys like the music, feel free to go to his Spotify and hit him up. Anyway, or his SoundCloud and hit him up. Anyway, thanks for watching, and I'll see you guys next time. Peace.